Welcome to our topic, electrochemistry. My name is Samuel Nyamu. From the diagram, we can see some of the products that are found in the market. We can associate with them, like the car battery, the dry cell. All this marks part of what we'll be learning in this topic. We can define electrochemistry. Definition of electrochemistry deals with the conversion of chemical energy into electric energy, and at the same time we can say electrochemistry is the conversion of electric energy into chemical energy. Electrochemical cells fall into one of the two basic types, the galvanic cells or the electrolytic cells. The galvanic cells convert chemical energy into electrical energy, for example, the batteries. And we also have the electrolytic cells, which convert electric energy into chemical energy. We can see a virtual experiments in our diagram where we have the blue copper 2 sulfate, then we have a strip of zinc metal dipped into this solution of copper 2 sulfate. What happens, we can see in our diagram that the zinc are moving into ions to form zinc ions while releasing electrons, while these electrons that are being released are being gained by the copper. A reaction occurs where we get zinc ions and solid copper being deposited on the zinc surfaces. At the end, the blue color of solution, the blue color fades away, and we can see that the solution in the first experiment we have a deep blue color of copper 2 sulfate, but in the second solution the color seems to fade away, and this is the reason because the copper 2 ions are gaining the electrons and gets deposited in the zinc rod, while the zinc rod dissolves into the solution to form zinc ions. This is an oxidation reaction. This is an oxidation reaction process where electrons are transferred from one chemical to another. One chemical loses electrons in a process called oxidation, while the other chemical gains electron in a process called reduction. In our virtual experiment, zinc loses electron and we say this is oxidation process, while copper gains electrons and we say this is a reduction process. Since zinc is more reactive than copper, the zinc will dissolve in solution, and we can actually see this reaction occurring. This reaction must be spontaneous, where the zinc dissolves into the solution, and therefore the blue color turns to colorless due to the zinc moving into zinc ions, and copper gains the electrons to form the copper solid. The reverse reaction, where we put copper metal in a zinc ion solution, is non-spontaneous. Redox reaction is a word coined from reduction oxidation reaction. We can see that each zinc atom gives away 2 electrons and to a copper ion to give us a copper atom, and zinc 2 ion in the spontaneous reaction shown in the diagram above. To clarify the redox process, we often break a redox reaction down into 2 separate stages we call half reaction. In one half reaction, a chemical loses electrons, which we say it is oxidized or oxidation. We call this the oxidation half reaction for zinc moving into zinc ion with a release of 2 electrons. We can see from a zinc atom which has a charge oxidation of 0, it's moving to a zinc with a positive 2. So in this case we say there is an oxidation reaction taking place from 0 to positive 2. Notice that we are effectively treating electrons as product of the half reaction. In the other half reaction, we look at the reduction half reaction, where a chemical gains electron. We say this is reduced or reduction. For example, we see copper 2 ion, or the copper ions will gain the 2 electrons that have been lost by the zinc to form copper solid. In this case, The copper ions has a charge of 2 and it is moving to an atom of copper solid which has an oxidation of 0. So in this case, we are moving from a positive charge of 2 to a charge of 0, and therefore we are saying this is a reduction reaction. The sum of this half reaction that we've looked above must give us the overall reaction of interest. If we add the oxidation reaction of zinc and we add the reduction reaction of copper, the left hand side we will have zinc solid plus copper 2 ions plus 2 electrons, which will be on our left side, and on our right hand side we'll have zinc ions plus copper solid plus 2 electrons. In general, we have 2 electrons on the left hand side and 2 electrons on the right hand side. If we cancel them, we end up getting an overall reaction. Why do we call them half reaction? Each half reaction is written so we can see what is happening to the electrons in the overall reaction. In reality, a half reaction cannot occur by itself to any great extent. The lost electron in the oxidation half reaction must go somewhere. The gained electron in the reduction half reaction must come from somewhere also. Two half reactions always work together to give an overall reaction that can occur to a great extent, and this is what we are referring to as redox or reduction oxidation reaction. In a half reaction, we said an atom can lose an electron to form an ion, which we are saying it is oxidation, and at the same time an ion can gain an electron to form an atom. Therefore we call this reduction. If you look at the equation given there, the M solid loses an electron to a process we term as oxidation, and the M ion can gain an electron on the right hand side to go back to the metal solid. We term this as reduction. The electrons stay on the metal electrode and never found in the solution. Since the chemicals are in direct contact with each other, the electron transfer occurs directly and we can't use the electron to do any useful work. How can we separate the chemicals but allow the electrons to transfer indirectly so that we can use them, as we've seen in our virtual experiment? It is possible to separate the solution and use the electron to produce a useful work. For example, in our chart shown, we've separated the copper and the silver, and only the electrons that are moving, but our solution are separate, where we have a solution of copper and we have a solution of silver nitrate, and only the ions, the electrons will be moving to produce a useful work, which can be measured by our voltmeter there. We'll be looking at a such illustration in our lesson. When a metal is dipped into its solution, we term this as half cell. For example, when a copper metal is dipped into copper 2 nitrate solution, we say that that is a half cell of copper. Also, if we dip a silver metal into silver nitrate, we term that as also another half cell. So a half cell is when a metal is dipped into its solution. The half cell reaction take place in separate containers. Since a half reaction cannot take place by itself, we need to connect two half cells together in turns. That must make a circuit. Two connections of two half cells will give us what we are terming as galvanic cell, which works, and this also we can call it as an electrochemical cell. When we connect two separate electrochemical cell, which we are saying they are half cells, we have one half cell of a metal dipped into its solution and a separate half cell of a metal dipped into another solution, then we can be able to get our electron moving, and in such a case we'll end up having a useful work produced by electron. We can be able to measure the voltage using our voltmeter, and this constitutes what we are referring to as galvanic cell. The left half cell has a solid copper electrode in copper ion solution, while the right half cell has a solid silver electrode in silver ion solution. So we have two half cells, one for copper and one for silver. A wire can connect the two solid electrodes for the electrons to move through. To connect the two solutions so that ions can move between the half cells, we require us to have what we are terming as a salt bridge, which is just another solution of ions. A salt bridge is made up of salt of potassium nitrate or sodium nitrate. A salt bridge is made up of a salt of potassium nitrate or sodium nitrate, potassium nitrate or sodium nitrate. The purpose of a salt bridge is to connect the circuit, so that our electrons can be able to move freely. Number two, the purpose of a salt bridge is to replace the used ions, So that is the purpose of a salt bridge. So in turn, we can see that our galvanic cell is connected, where we have a wire connecting it to a voltmeter into the other solution of silver nitrate, and from silver nitrate to copper nitrate we have a salt bridge, which we've said it's made up of either potassium nitrate or sodium nitrate, and we've said the purpose is to connect or to complete the circuit and also to replace the used ions. Oxidation occurs at the copper electrode, which gives the special name of the half cell as the anode. Since the anode collects the electrons that are lost, it has a negative charge and leaves the anode. So we have copper solid, it loses the electron to form copper ions. The copper solid loses the electrons to form the copper ions, and at the end, since it is losing electrons, we'll see the anode being worn out. We'll see the anode being worn out. Electrons move from the anode to the silver electrode through the wire. We can get them to do something useful, like light a bulb. Can also be measured using the voltmeter as shown in the diagram. Reduction occurs at the silver electrode, which we give the special name the cathode. Reduction occurs at the silver electrode, which we give the special name the cathode. Since the cathode collects the positive silver ions, they can gain the electrons. The cathode has a positive charge. So we have the silver ions, which we gains the electron to form silver solid. The positive ions leaves the anode, the left hand side, while the cathode, the right hand side, collects the positive ions. Alternatively, the negative ions collect at the anode and move away from the cathode. The ions are free to move through the salt bridge and are required to complete the circuit, as we had said, as one use of the salt bridge is to balance the ions. Therefore, the electrons are being lost from the left hand side and are being gained from the right hand side. Overall, negative charges, or the electrons and negative ions, are moving clockwise from the left hand side to the right hand side as shown by the arrow. Positive charges, or the positive ion and electron holes, are moving counterclockwise. The positive charges and electron holes are moving counterclockwise. In general, the electrons move from the anode, from the left hand side, to the cathode in the right hand side. The overall reaction is exactly the same as when we place solid copper in a silver solution, but since we have separated the half cell, we can look at the separate half reaction as they occur. We have the copper solid moving to copper ions, releasing the two electrons, while the silver ions must gain the two electrons. That's why we are multiplying by 2 to form silver solid. Note, for silver it has only one electron that it must gain. Therefore, we have to multiply with 2 to form 2 silver ions in our second half equation. Therefore, we'll have copper solid plus 2 silver ions. If we sum up what we have in the left, plus the 2 electrons will end up giving us copper 2 ions in the right hand side plus 2 electrons plus 2 silver ions. Since we have the 2 electrons on both sides of the equation, we can cancel them so that our overall equation will be copper solid plus 2 silver ions plus copper ions plus 2 silver solid. This is our overall equation reaction. Shorthand notation for galvanic cell or an electrochemical cell. Drawing a diagram for galvanic cell or describing it as we've done in our previous discussion is too time consuming to do on a regular basis. We can use a shorthand notation. For example, we have copper, our overall equation, which is copper solid plus 2 silver ions, giving us the copper ions plus 2 silver solid in our right hand side. We can put that in a shorthand to represent our galvanic cell as shown below, where we have the copper solid with a slash copper ions with a 2 slash silver ions with a single slash silver ions, whereby the single slashes refer to half cells, while the middle 2 slashes represent our salt bridge. The 2 slashes at the middle represents our salt bridge. So this is a representation of what takes place in a galvanic cell. We've said a single vertical line or a slash indicates a charge in phase. We say it's a half cell, like that between a solid electrode and the solution it is immersed in. And double vertical line indicates a salt bridge. What is not shown in the shorthand but is always amplified is the wire connecting the 2 electrodes to complete the circuit. So we can be able to write our galvanic cell in a shorthand as shown above. If we read the shorthand notation from left to right, it says a solid copper anode in a solution of copper 2 ions, which is connected by a salt bridge to a solution of silver 1 ions, into which a solid silver cathode has been placed. The electrodes are connected by a wire. We can read the notation as a solid copper anode is in a solution of copper 2 ions, which is connected by a salt bridge to a solution of silver ions, into which a silver cathode has been placed. The electrodes are connected by the wire. We always choose to write the cell notation with the oxidation reaction first and then the reduction reaction. This means the leftmost chemical in the cell notation is always the anode, while the rightmost chemical is always the cathode, just like in our galvanic cell. Additionally, the electrons always flow from the left to the right through the wire, which is the way we read the shorthand, just like we had illustrated in a galvanic cell. In summary, we can write our cell notation for zinc and copper as shown below, where we have the anode half cell on our left hand side, then we have our cathode half cell in our right hand side, and then in the middle we have a salt bridge with the double sticks, and then we have the phase boundaries, which represent our half cell with a single stick. Electron flow this way from the left hand side to the right hand side. We call this a cell notation, which represent the galvanic cell. We will continue in the part 2 of our electrochemical cell in our next lesson. Thank you.